Okay, let's work through this practice exam. I think I have, yep, here's the data. So let's start this guy. All right, so the first one we have to build these confidence intervals for this variable wage start. So here we go, let's do this. Insert. Put number 1 right here. So first we need a point estimator. This with the x bar equals average. Remember, confidence interval just has a point estimator plus or minus a margin of error. So there's a point estimator. The margin of error, in this case, we learned 3 different ways to build a confidence interval. If we had a population standard deviation, then we could find the margin of error using the confidence.norm function. But in this case, we haven't been given a standard deviation, but we can find it, which is this equals standard dev function, right? Or the standard dev.s. There it is. So the margin of error then is equal confidence. Oh, I'm feeling better already. Confidence, and then ask for an alpha. In this case, our alpha for the whole exam was 0.05. Standard deviation, there it is. Oh, the size. I don't have the size yet. Let's see. Let's put it right here. So let's see. N equals count. I think it was 344, but I can't remember. 344, yep. All right, so upper confidence limit and then lower confidence limit. So the upper confidence limit is x bar plus the margin of error. The lower confidence limit is x bar minus the margin of error. All right, so there's number 1. This is 1A. Here's 1B. So 1B says do the same thing, only this time do it for this other variable, wage st, this variable right here. So I can actually, if I hit F2, so I just copied this guy and pasted it right next to it. So it's actually building a confidence interval of the variable right next to it, this employee F2. That's not what I want. I actually want wage S2, so I can just grab that and drag him over. And that's what I do. And that's it. Everything else is the same. So the count is actually a little bit different. But it doesn't change the answer that much. That's because there's some missing data in here. All right, so that's 1. So let's do question 2 now. Question 2 is another confidence interval question, but it's asking for confidence interval around a proportion. So 43% is a p hat. So p hat, in this case, 0.43. We actually might as well be just doing this one too. 0.40 is the next question. It's the same thing, 0.40. So let's just do it all together. So in this case, the margin of error, we can use the confidence.norm function. Let's see how this looks. Confidence.norm function. It's going to ask for an alpha, 0.05. We can use that because this is a proportion. So when we're dealing with proportions, we can assume normal distribution if our n was greater than 30 and if n, number of successes was greater than 5, number of failures greater than 5 too. So here we go. We got alpha. We're going to put the standard deviation right there. It's not there yet. And then we're going to put the sample size right there. So let's do this. This is n. This will be our standard deviation. So the standard deviation of a p hat is just the square root of p hat times 1 minus p hat. And that's it. And n, well, it's the same as up here. So I'm just going to equals 344. All right. Let's see, let's just key this in. So now I can just copy these guys over here. This is actually still 344 in this case. And I'm done. So not quite, actually. Upper confidence limit, lower confidence limit. Upper confidence limit is p hat plus the margin of error. Paste that over. Lower confidence limit is p hat minus the margin of error. Paste that over. So that's it. So between 48 and 37%, and between 45 and 34%. All right. Let's make sure I do this right. Looks good. All right, question 2. Now let's do question 3. Assume we want a margin of error of no larger than 0.03. So that's what we call B, 0.03. Solve for n. That's what it wants to do. Solve for n. So we want a new margin of error with a B of 0.03. So to solve for n, remember there's this formula that's something like n equals So your numerator would be like z times sigma times the standard deviation divided by b, where b is the desired margin of error. All of that squared. Something like that, right? So I need a standard deviation, call it S, and I need a z. So we're doing a 95% confidence interval. So the z for a 0.05 alpha, or 95% confidence interval, is 1.96. Standard deviation is the same one that we just used up here. I mean, we could calculate it again, but it's the same thing. It's the square root of p hat times 1 minus p hat. So the problem says to use the same thing that we used up there. So that's it. So then we could just say, all right, well, this is, let's see, z times my standard deviation divided by b, all of that squared. And then we actually always round up. You don't have to use the round up formula, but there it is. 10,047, or 1,047. All right, so that's 3. Let's go on number 4. During this time of the study, we read in the press that the average number of total employees in each store is expected to be 25. We suspect this number is low, and we want to use our sample to provide evidence that the true average number of employees is greater than 25. All right, so we talked about this one in class, but the null hypothesis then is that it equals 25. So there's really only 2 options here. And we want to show that it's actually greater than 25. So there we go. It's that one right there. Done. Number 5. So this is a 1 or 2 tail test. It's a 1 tail test because we only in the alternative hypothesis, we just care about one side. The t-score. All right, so let's do this. So we're looking at the total employees. So total employees, we have to first, it talks about this in the question. We have to first make the total employees column, which is the sum of these 3 guys right there. Full-time, part-time, and number of managers. All right, so this is question number 5. Okay, scroll down a little bit. Question number 5. So it's asking for a t-score. So remember, t is this is like a what you got minus what you expected divided by some standard error. All right, so what you got, what does that mean? So what you got is the x bar, what the average was. What you expected comes from mu, right, from the null hypothesis, which was 25. So x bar equals average total employees. That's what we're dealing with here, total employees. So the total employees was 30.34. What you got minus what you expected by some standard error. So remember, the standard error was something like, let's see, standard deviation divided by the square root of n. All right, so I got to have n, and I got to have the standard deviation. Call it S. Okay, let's do the standard deviation. Equals st dev. Oops. And n is 344, so I've got that down. So standard error then is the standard deviation divided by the square root of n. Yep, that's what I meant. And then finally the t in this case. A little bigger. T then is what you got. Let's see, let's put this in brackets for the numerator. What you got is that guy, 30.34 minus what you expected, divided by some standard error, 7.78. So that's pretty big. So then to find the p-value for that, which is the next question, is we use this t.dist function, t.dist, and it's actually the right tail, right? Because we're caring about something that's bigger than what we expected. That's the right tail. So that just says, well, give me an x. Really, it's asking for a t. And then the degrees of freedom is just n minus 1. Oops, n minus 1. There we go. So that p-value is essentially 0. So what does that mean? Well, that means that we can reject the null, and we say, yes, there's actually evidence that enough evidence to say that the average number of employees is greater than 25. So my theory is justified. All right, so that's 5. Let's look at 6. So this essentially, we got to figure out a couple things here. This is to determine changes between New Jersey and Pennsylvania. We have to figure out what's the null and alternative hypothesis. Well, the null is that they're the same. We talked about this one in class 2, so I'm not going to talk too much about this. They're the same, so it's got to be one of these equal times. So the only other thing that's left is to figure out, is this a pair of 2 samples? No, it's not paired data. We're comparing Pennsylvania data versus New Jersey data. So it's not like the same restaurant at 2 different states. It's just completely different restaurants. Pennsylvania and New Jersey. Different, not paired data. So we have to decide, is this equal variance or unequal variance? So in order to do that, you remember we have to do this F test for 2 sample data. So this is the variable that it cares about, change in employees. You can tell that because it says here, mean change in total employment. That's this variable, change in employment, which is actually, as you can see, it's a calculation that I have running in here. So I did the calculations for you. We talked about in class what it means. It means after, how many employees do they have after this trial and before this trial? How did it change? If it was a positive number, then that meant that they hired people. If it was a negative number, that they meant that they fired people. All right, so we first sort this by state. And then what I'm going to do is create a new tab. Whoops. And then I'm going to call one New Jersey and one Pennsylvania. And what we're going to do then is, let's see, 0 is Pennsylvania. Is grab all the 0 data and put it in the right column, Pennsylvania. So here we go. That's from 0 up. Control copy. This is Pennsylvania data. Oops, see, if I just paste it, I get zeros in here. I have to do paste special. Forgot about this. And I just want the values, this 1, 2, 3 thing. Because there's an actual formula in there, where it's just adding and subtracting some cells. Well, if I copy and paste that over there's no cells over here for it to add or subtract. So this is what I want. All right, and then let's find all the ones, which is the New Jersey data. Control copy, put it right here, paste values. All right, so then we have to do this data analysis. We're after the F test, 2 sample for variance. There it is. Variable 1 range is New Jersey. Variable 2 range, Pennsylvania. I got labels going on there. Let's put it right in here. Hit enter. All right. And then we just go 0 in on this p-value. This is a low p-value. So if it's a low p-value, then we say, oh, this is unequal variance. Because the null hypothesis is that they are equal variances. So we can reject that null and say, well, they must be unequal variances. So that's it. So then the next step, the next problem, it says, okay, now actually go do this. So let's just do that. So 2 sample assuming unequal variances. That's the one we want. Variable 1 range, these guys. Variable 2 range, these guys. Labels, yep, hypothesized mean is 0. And let's put this right below it, right there. That's it. All right, so let's take a look at these results. Here's our means for New Jersey. So have a negative 6.7. That means on average the store is fired, 2/3 of a person. In Pennsylvania, they hired almost 2 people on average during the same time period. Is this significantly different? Or is New Jersey significantly smaller in this case? Yes. There's a p-value of 0.04, which is lower than 0.05. So we can reject the null. That the null says that they're the same, that they should be the same, and say that there's evidence that no, in fact, Pennsylvania is bigger, or New Jersey is smaller. That's seeing the same thing, right? All right, so that's it. That was 6 and 7. We're on to the serial data. Okay, so let's do the first thing is do a simple linear regression with sugar as our predictor. And we want to predict, doesn't say here, but we want to predict the ratings. So let's do this. All right, so I actually figured this out in one of the classes. If I highlight sugar, Control-Shift down, and then actually it's even easier. If I just select H here and then hold my Control button and select K, it's actually selecting both of those data. And then say Insert, Scatter Plot. There it is. It's done. So that's it. Right-click and say Add Trend Line. And then this little thing comes up, say display equation, display r squared. Stick this right here. So r squared is 0.577. Our equation is, this is written backwards, 59.28 minus 2.4008 times sugar. Right, so that means for every gram of sugar, I would reduce my rating by 2.4008. Yeah, so that's what that means. And the intercept, you see where it crosses, is 60. Right, approximately 0.59. This is ratings, right? We're trying to predict ratings. I know this is ratings because ratings goes from 0 to 100, where sugar goes from 0 to 20 or something like this. So in this case, I always want my y variable here. What is I'm trying to predict on the y-axis? Remember y, this is how I remember. Y goes to the sky. Y goes to the sky. That's how I remember which one is y and which one's x. Y goes to the sky. All right, so this is the right way. So then it asks, well, what happens if I have a 5 grams the sugar, a cereal that has 5 grams of sugar? Well, I can just easily estimate what it is. So it's 59.28, 59.284. That's my intercept, plus 5 times negative 2.4008, right? Or I could just say minus 5. Instead of saying plus 5, I could say minus 5 times 2.4008. Same answer. 47.28, right? So that's that. So it drops, right? So it goes down 5 grams. We figure that out. All right, now let's do this regression with all this stuff except for without these dummy variables. So let's do this data analysis, regression. Okay, my y variable is the rating, and my x variable are shelf, sodium, potassium, vitamins. I got labels here. Let's put this in a worksheet called Model 1. Click on residuals in case we need it, and that's it. Okay. All right, here's my r squared. I think that's one of the questions. Ask for the coefficient for sugar, I think. Yep. Is overall test significant? That's what we could look at this guy. Yep, we got a low p-value for the significance f. And then it's going to ask for the significance for all of these. So I can do this home, conditional formatting, highlight cell rules less than 0.05. There we go. So they're all significant except for potassium. Here's the coefficient for sugar. What does that mean? That means for every increased gram of sugar, I would expect the score to decrease by 1.84 if all things else were held constant. All things else were held constant. All right, so here we go. If I create a cereal with no fat, no sugar, no sodium, but 10 grams of fiber, no potassium, and no vitamins, what do you predict Consumer Reports would rate it at? So remember, these coefficients, I can use these coefficients to come up with an equation that will predict things, right? With an intercept, and then the amount of fat times negative 0.34, the amount of sodium times negative 0.04, the amount of fiber times 2.9, on and on and on. So my question is, all right, make a cereal that just has fiber in it, nothing else. So it's intercept plus 10 times the amount of fiber, because it says 10 grams of fiber. So 10 times the coefficient of fiber is a better way of saying that. There we go. Answer is 90.98. All right, so that's it. Then you're supposed to watch this commercial. All right, let's add a few dummy variables now. Let's go back to the data. So I'm going to include, so I got to remember, 3 variables for, is it 3? I got to look. Yeah, 3 variables for the manufacturer, 1 variable for the type of cereal, hot or cold, and 2 variables for the shelf. All right, so the type I'm after are Quaker, Kellogg's, and General Mills. So Q, GK, and General Mills. I want cold cereal because I want I want hot cereal to be my base case. Yep. And first shelf and second shelf. All right, so let's see if I can do this all at once. So equals if, remember we're making dummy variables. So if this guy right here, and I'm going to lock in just the B column. So I'm going to hit F4 a couple times so that I get the dollar sign just right in front of the 4 equals this guy. And now I just want to lock in the number 1 so that it doesn't move up and down, but it'll stay on that first row. If that equals 1, then I want it to be 1, otherwise 0. All right, so I should be able to copy and paste these guys over. Yep, looks good. Looks good. Now if I copy it one more time, it's still over here in the manufacturer, but I had just grab that, move it over. That's what I want. And then do that again, but instead of type, I want it on the shelf. So you don't have to do it this way. This is just a fast way of doing this. I just know I can do this pretty quick. So there we go. That's working. So you can like sort of check and go all the way over. Again, don't do this so fast if you don't know what I just did. Just make dummy variables like we learned in class, right? That if it's Quaker, then it's 1, otherwise 0. If it's Kellogg's, it's 1, otherwise 0. If it's Granite General Mills, 0, other ones, right? I did that. I just did it with sort of these cell references with the dollar signs and all that junk. So you can go pretty fast if you want. All right, let's do this again. Data analysis, regression. Rating is our y variable. It's moved over, so we got to change that. And then my x variables, starting with Quaker, all the way over, all the ones we included last time. Hit enter. Labels, yep. Let's call this model 2. And click on OK. All right, so here's our adjusted R squared. So it went up a little bit, but not a lot. Overall significance, yep. Let's look at the p-values for all these guys. Home, conditional formatting, highlight cell rules, less than 0.05. So the same ones that were significant before are still significant, so that's a good sign. We'll find out in a minute. There's not a lot of multicollinearity going on. If there was, then these might change, but there's not. And there's hardly any of these dummy variables are significant except for Quaker. So, and then this is the coefficient negative 2.79. So what that means is that all else being equal, if the cereal is made by Quaker Oats, it is going to have a decreased value compared to, what does that mean? Compared to the base case. Well, the base case is all other cereals that are not Kellogg's or General Mills. Okay. All right, so then it says, okay, so we're going to do this in a minute, so let's just do it. We can find test the scatter plot for linearity and equal variance. So we talked about in this class that I would probably say that there's some equal variance problems going on here, because I kind of got like this sort of diamond shape coming up here. Kind of gets big, kind of gets big, gets small. So the variances kind of go up and then come back down. So I'd say maybe there's an equal variance problem here. Linearity, I wouldn't say there's any problem. There's no like curve going on in the data anywhere that I can see visually. So one thing you should not do is don't try to add a trend line in here. That trend line will always be on 0. Even if there's a curve, it'll be right on 0. Even if you do like some polynomial and stuff like that, it's probably not the best way. Really just eyeball this and see if you can see something. So I would say, yeah, equal variance is probably broken, but linearity is okay. All right, so let's look at, next is a histogram. So just check for normality of these residuals. Leave the bin range empty. We've got some labels going on there. We want to check the chart output. Click on OK. All right, so here's our histogram. Make it a little bigger. Yeah, it looks pretty good. I mean, this is good enough, essentially. We just want it kind of around like a normal distribution, it sort of should look like. So it's not perfect by any means. This more should probably go out a little bit. But and there's some like guy way early on here. That's okay. So it looks pretty good. In fact, you could fix this, right, the way we've learned in class to sort of move this one way over here, and then it would look even better. So I'd say, yeah, normality assumption holds. So the last thing to do then is to check for multicollinearity. Whoops, wrong data. All right, so if you remember how to check for multicollinearity, then we want to go and check the correlation coefficients, correlation matrix of all our variables. So starting at Quaker Oats all the way over, we don't include ratings, right? So we don't want to include our Y. There we go. Labels in the first row. And this is going to be our VIF worksheet. So remember, I can copy this guy, paste him right below. Just copy the numbers then. Paste the numbers right there. I can say paste special, and then say I want to transpose and skip blanks. Okay, then we get it all. Highlight all this stuff. I can delete it. I can say equals M inverse. Come up here, highlight the data, just the data. Control Shift Enter. Got it. Now on the diagonals, go like this. And we say our average is really low, you can't see this, but it's 2.735. It's below what the screen is being captured. And then none of these are above 10, so we'd say, yeah, there's no multicollinearity. Fiber has the highest, 8.13. I think that's it. I think I got through everything. Anything I missed here? Yeah, so is there a significant difference between the third and first shelf? No, because the variable for first shelf is not significant. There is a difference, though, for Quaker Oats, and the control variable, or the base case of all other cereals, because it is significantly different. Did this. There's not evidence. So there is not evidence, so I would say false down here. Done. All right, so that was it. So you guys are going to do well on this exam. Don't do it as fast as we just did it. And don't worry about it if you can't do it that fast. This was speedy, right? So this was just to give you another view of what this exam it was like in a real quick version if you needed to look through some of the parts that we missed. All right, see you later.